The force between current carrying conductors. If we have a wire carrying a current towards us coming out of the screen, it has a magnetic field around it like this, given by the right hand grip method. Pointing your right thumb in the direction of the current, your fingers curl in the direction of the field lines. If there's a current going away from us, we have the same pattern, but with the field lines in the opposite direction. We can represent the same situation from the side. Here we have wire A carrying a current up the screen. Using the right hand grip method, if you point your right thumb upwards, your fingers will point towards the screen on the right hand side of the wire, producing a field into the screen like this, and come out of the screen on the left hand side of the wire, producing a field coming out of the screen. If we now place a second wire B, also carrying a current up the screen, using Fleming's left hand motor rule, this wire will experience a force. If you point your first finger in the direction of the field, that's into the screen, your second finger of your left hand points upwards, representing the current direction. Your thumb then will point to the left towards wire A. This represents the thrust or the motion of wire B in this direction. By Newton's third law, if wire A is exerting a force to the left on wire B, then wire B will exert an equal force in the opposite direction on wire A, and the two wires will be attracted towards each other. If instead we place the second wire on the left hand side here, again carrying the current up, now by Fleming's left hand motor rule, your first finger of your left hand points away from the screen, your second finger again points up, and now the thrust or motion will be to the right, causing a force to the left on the first wire. So again, the wires are attracted. If we have a wire carrying a current in the opposite direction, as shown here, now using Fleming's left-hand motor rule for this wire, your first finger again points towards you, the second finger now points down in the direction of the current, and your thumb will now point to the left, producing an equal force in opposite direction on this wire. And now the wires will repel each other. So two long straight wires carrying currents in opposite directions repel each other, and two long straight wires carrying currents in the same directions attract each other. If the two wires are a distance r apart and carry currents I1 and I2, the field from wire 1 around wire 2 will be given by B is equal to mu naught I1 over 2 pi r. The force on wire 2 due to this field is given by F is equal to B I2 L. So we can combine these to give the force as mu naught I1 I2 L over 2 pi r. This equation actually gives us the definition of the ampere as the steady current which, when flowing in each of two infinitely long, straight, parallel conductors with negligible areas of cross-section and are 1 meter apart in a vacuum, causes each conductor to exert a force of 2 times 10 to the minus 7 newtons on each meter of the other. Here's an example. Calculate the force between two parallel wires of length 3 meters, a distance of 15 centimeters apart, if each carries a current of 2.5 amps. Well, this is the equation we need. Putting in the values, the permeability of free space given on the datasheet as 4 pi times 10 to the minus 7 henries per meter. You'll notice now how this pi term in the permeability of free space cancels out with this pi term in the equation. We have the current in I1 and I2 being 2.5 amps. The length was 3 meters, and their separation 15 centimeters or 0.15 meters. This gives a force of 2.5 times 10 to the minus 5 newtons.